object safely. So we just create something, a bubble around the object. So this is the robot, and when it know that if it move along that direction and if the object is in that direction, it can avoid. So the robot still moving on the same direction. And then we need to calculate the time that it's going to collide. So something like this is the timing that we create. So it's going to be a fuzzy vector for the timing that the time of the collision, so that we know that if the robot keep moving this direction and if the object keep moving that direction, somehow it's going to collide at some point. So this is the time that it's going to collide, collision time, right? So what we do is that after we calculate all those things, we need to find the free sector so that the robot know that where is the free sector along the path. So suppose the object is on this side, so the free sector is going to be on this side. So if we have two objects, something like that, the free sector is going to be this side or on the left side or on the right side. It depends on the goal. And so what we do is that we just have a fuzzy rule base to calculate the direction of the robot and the velocity of the robot. So the input for fuzzy inference system is the robot direction and then dangerous value and then a robot speed. And the output is going to be a velocity and the angular velocity, something like that. And this is the fuzzy set inputs. We use a type 2 fuzzy set. So this is somehow the example of the rule base. So if like d angle is 0 big and dv is medium high and vi is fast, then we need to decrease the velocity of the robot. Or if the angle is 0, dv is 0 high, vi is 0 fast, then va of the robot is approach 0. So this is when we do the simulation. Suppose the robot, it need to move to this green point, and this is the obstacle. So it's able to avoid the obstacle. If we have more than one obstacle, it's still able to avoid that obstacle. And this case is we don't know the velocity of the obstacle is unstable. So everything has to find the free sector. So it's not going to be as easy as the previous example. So now we implement this algorithm into this real robot, and this robot we get it from a defense technology. So it's try to avoid this table. And it see this obstacle as something. Yeah. So that's why it need to move a little bit, and it needs to go to this stop point. So now it's gonna move past the drawway. So it see the draw that this side is an obstacle. So this is what the robot see. So now it's try to avoid, and it see this obstacle. Okay, now so now we want to use the fuzzy set into the feature extraction. So in the synthetic aperture radar, because what in this application we want to classify the tank. There are three type tank. So if you look at the synthetic aperture radar image, you can see that even with our eye, we cannot classify them from each other, right? So what we do is that we create somehow our fuzzy current matrix. What we do is that we have a gray image, and then we do a fuzzy seaming. So in order to do the fuzzy seaming, you can use as many as cluster as you want. So suppose we have 3 clusters. So what we have is that we will have 3 pane for membership value for each cluster, right? And then after that, we calculate at each pixel what cluster that pixel belong to. After that, we do something similar to a gray level co-current matrix. So like suppose in this, if we look at this direction and we're looking for only what cluster 1 and cluster 1, and what we do is that we do the summation of every pixel that fall into this same condition. And then that's why we create a plane that we call FCOM plane. So if we have 3 clusters, then we have FCOM, 3 FCOM plane. If we have 4 clusters, then we have 4 FCOM plane. And then after we get all this plane, we calculate a feature, just like what we do with a variable co-current matrix. So this is the example of the feature that we have. So if we only use 0 direction, and if we only use FC1 to FC4, and if we have 2 cluster, then the feature number is going to be 8. If we increase the number of cluster, then the feature number will be increased also. So this is one of the disadvantage of this algorithm, because if we increase the number of cluster, the number of feature will be increased. If we have more direction, then the number of feature will also be increased. So after that, what we do is that we just use a simple classifier, which is support vector machine and linear basis function. And then after that, we do the ensemble average. So this is the parameter setting that we have. So this is the plane that we have. So in this case, we have 8 cluster. So in each cluster, we will have 1 FCOM plane. After that, we use this plane to calculate the feature. So after we run the classifier, we will see, you can see that the base value of recognition is actually from FCOM feature. So it's a little, I think I would say that it will be better than GLCM. This is the result from the training data, and after that we use it into the blind test data. Blind test data is that the data that we kept outside of the training. We don't use this for the training. So in this case, still that FCOM feature gives us a better result than GLCM feature. So this is just somehow use the fuzzy vector, fuzzy set into the generate feature extraction. So now this is a classifier that we developed here in our lab. So in this classifier, what we call is that learning vector quantization inference classifier. So it's actually neural fuzzy. So what we have is we have 4 levels. The first level is actually a input feature. Second layer is actually a prototype layer. The third layer is actually a Lua inference layer, and then this is actually a dot product between the value from this layer and the weight. And then we have the output layer. So the output layer is actually the aggregation layer. So layer 1 and layer 2 is we have sorry. Layer 1 is we have an input sample, and it has a F feature. And then suppose we have M class. So, and then we have P prototype for per class. So the total number of prototype will be Q. And then in the first layer is an input feature. So normally when we run this classifier, we will normalize the feature so that the value of the feature will be between 0 to 1. And then in layer 2, we calculate the process prototype and then the process feature using Euclidean distance and then find the minimum. So which one gives you the minimum Euclidean distance, then that one is the winner. And then for each feature, we also calculate a winning feature also for that prototype. So you have a winning prototype and also a winning feature. And then after that, we have two methods to calculate winner takes all. The first method is just that the winner will takes all, right? That's just the same as you do with LVQ. For the solve method is that we calculate a membership, a value or the confidence of the winner. And then after that, at the output layer, so we calculate our H vector, which HJI is the value that we get from mu G multiplied with mu F. So it's just kind of like a winning from the prototype and winning for the feature that give you this value for output vector. And then at the output layer, we just do the dot product between H and W. And if YL is the biggest value, then the class of that sample will be L. L class, just as normal way. So when we update our prototype, this is the prototype update equation. So the prototype that got updated is only the winner one. And then for feature I, the winning feature that we select will also be updated. Okay. And then for the weight multiplication, since this algorithm only use we set a regulation is that the weight in the output layer, summation of all the weight has to be equal to 1. So it will be you have to it will be normalized by this summation. So the cost function of the weight update is the same, similar. It's just some square error. And then after we do the calculation, we get the update equation for the weight, something like that. This is the algorithm of it. So what we do is that we find FR, which is a summation of the weight of Ri, and then we initialize TOPC, SLF. So SLF is just a select feature. So first, it's going to be 0, right? And then cow is equal to 0. Fs is the set of feature to be select, so it's going to be empty set. And then the algorithm will be repeat by picking I feature from the remaining feature, and then keep I feature in Fs, and then after that, set C to the classification rate. And if C is bigger than TOPC, then update TOPC and SLF. And until there is no more feature, this loop will be repeat. And then after that, at the end, we will get the feature that we select out of of all the feature, right? So this algorithm actually do both feature selection and do the classifier. And then next is doing the select weight. So what we do is that pick W that connect to the remaining of Fs, and then keep weight in WS, and then increase the count. And see if C is bigger than top C, then update top C and SLW, right? Until there is no more output weight. And then after that, we will get WS. So in the end, we need to classify the features. So we have two rules, either using the Cripps rule or fuzzy rule. If we use a Cripps rule, then if at xi is close to gji, then the class of the feature will be k. For the fuzzy rule is that if wkji multiply with this fuzzy set, then the class will be k also. So the test vector will be assigned to the consequence side of class of the rule that give maximum output of the antecedent. So after we have all the rule, we calculate the conclusion of all the rule set, and then which one give you the highest one, then that test vector will be due to that class. So what we do is that we actually run this algorithm on the LBCL and GLI dataset. This two dataset is actually from UCI dataset. The first one has 4,000 features, 4,000 dimension, and there are only 47 samples. So this is kind of like a very high dimension and small number of sample. And GLI is 22,000 something and only 85 sample. So what we do is that after we run our algorithm, for the LBCL, we get only a select feature is 16, and this is the number of feature that we get out of that the LBCL. And for GLI 85, we get 15 feature, and this is the 15 feature that we have. And we actually check if the feature that we get is similar to or the existing algorithm that they run on this data set or not. And it's actually, some of them is actually similar to those previously research that done on this two data set. And it's actually similar to what has been confirmed by the biology that this feature set is some of the dimension is actually the feature that they use into classify a patient that they have this disease or not also. And this is the rule set that we get, right? And from the result, we can see that we have the best recognition rate, we get like about 100% with only 16 features. But on the average is like 90 something, 89 something. For the another data set, GLI 85 data set, we have select 15 features. The best one we get 94%. For the average one, we get 86 something, right? So if we look at the accuracy, I would say that it's comparable with previous one, right? But we get a smaller number of features that we select from the data set. Okay, so the previous talk is actually show us how to use a fuzzy set in some of the data analysis, right? But the last part of the talk is that synthetic pattern recognition, which is normally when we do the pattern recognition, the vector that we have is actually a vector of a number, right? But what if we don't use a vector of number? I mean, like, what if the number doesn't have any meaning in the calculation? So that is the problem of a synthetic pattern recognition. So what we do is just something like this. Suppose you have like a shape like that, and then you have a structural analysis that translate a shape into a sequence of a character. And then those sequence of a character are what we call a symbol sequence. We feed it into structural measure. And in that structural measure, we have like a class structure. And then after it matched, it will say that this shape is belong to what class. So this is actually what we use in synthetic pattern recognition, right? So it's actually similar to that. We have a shape like that. And then we need to encode, which is a primitive encoding. And then after that, after we do the primitive encoding, we will get a sentence or a string or a tree or a graph. And then we will pass it to a parser, which has a grammar. So like class 1, we have a grammar that is different from a grammar from class 2 or grammar from class 3, like that. So each class will have its own grammar or language. And then this sentence belong to what grammar, which grammar, then that sentence is belong to that class. So something like that. So this is a synthetic pattern recognition. But the problem is that if we use a synthetic pattern recognition like that, we have to specify a grammar for what, for each class, right? And it has to perfectly match with the grammar or the language of that class, so that it will say that this object belong to what that class actually. So it has to be like a perfect match. if it's because but we know that in pattern recognition we don't have a perfect match, right? Even though object is in the same class or the same cluster, the shape is not actually a perfect match of every object in that class. This might be a slightly a verification or modification. So if we use like this idea, like if we need a perfect match to say that this is belong to what card, then we cannot get a pretty good recognition rate, right? So what we do is that we just use generalize same old algorithm to make it work in string gamma. So in this case, we just use it in a facial expression application or face recognition application. So what we do is that something like this. So suppose this is the face that we want to recognize, or we calculate the average out of it, and then we do a different feature. So each face here calculate different with this average. So we get each of the difference, right? And after that, we do the normalization by divided by blur image, and then we get this image. And then after we get that image, we calculate, we create a string out of it. So by when we want to create a string, we need to match each sub window into a primitive symbol, right? So we actually calculate a gradient of each sub window. So we get the direction of each sub window. After that, we calculate the each gradient. We use a histogram of the gradient of the sub window. And then if that histogram, we have an image of a person, and that image of a person, we calculate a string of it, and then we kept that into a database. After that, after we have a test image come in, what we do is that we create a string just like what we did in the train data. And then we calculate a distance. Since a string, even though we have a string like this, even though it is a number, but it doesn't have a meaning in the arithmetic calculation. So we cannot calculate the Euclidean distance or any other type distance that we do with a vector of numbers. So what we do is that we need to use what called a Levenstein distance. So the Levenstein distance is actually a minimum number of transition between two strings. Transition, meaning of transition is that a substitution, deletion, and addition. So after we calculate a distance of the test string with all the string in the database, we need to calculate a membership of testing into a class. So what we do is that we get k nearest neighbor of the string that nearest to the test string, and then we calculate this equation. So it's like Uij is the membership of a string j that has membership value of string j in the class I. So each string in the training data will have this membership value in each class. So after that, we of the case thing that we get for the nearest neighbor, we will get ui of the testing. So which class that testing has the maximum membership value, then that testing will be assigned to that class. From this, just like this, X will be assigned to the class I. If UIX is bigger, is the biggest among the k nearest neighbor. So this, we run our algorithm with this 5 data set, and we can see that only Georgia Tech data set that we get lower classification rate. So in because in this data set, there's something different from the other data set that we cannot catch on with this algorithm. But when we run this algorithm, the same algorithm with a facial expression, we have 1, 2, 3, 4, 5, 6, 7, 8, 7 expression from the data set. So what we have is that we for anchor and discuss, this to give lower classification rate than the other two. And but the rest, I would say that is comparable with the previous method, even though we didn't calculate it as a regular pattern recognition, we calculate it as a string calculation. So one more thing of the string is that even though we have a comparable result, but when you look at the prototype of the string, we actually mapping the prototype back into the same signal, right? The previous signal. So we had the same shape, right, of the object. So then next application is that we use it for sign language translation system. So the system is going to be something like this. Suppose we have an input video, right? So what we do is that we select a frame from a video sequence, and in each frame we calculate a string using a shift command, a shift algorithm. So that from shift algorithm, after we match key point descriptor, so we get we match that key point descriptor to a character that we have, and then we get a sequence or a string sequence from each video, and then that symbol sequence is as our training data set, and then we feed it to string gamma UPC median to do the clustering, and then we have a prototype. So each side we have multiple prototypes for each side. So after that, if we have a test data come in, test data will come as an input video also, and then we select the frame from the video, and then we feed it to shift algorithm, and then we get a sequence of the test video, and then that test sequence is actually a symbol sequence for the test data, and then after that it will do the fuzzy k-nearest neighbor, just like what we did in the facial expression, and then we will know that the test string that come in is what size, right? So, but the question is that when we select a frame from a video sequence, it actually doesn't have to be the same number of frames, because this is one of the advantage of the string gamma, because like you don't have to have the same number of primitive symbol inside a sequence. Like one symbol sequence for one data, it can be 20 symbol sequence. It can be 20 symbol inside the sequence. In the test data, it can be 30 symbol inside the sequence. So it doesn't have to be the same number of symbol. So it's not like HMM. So the algorithm that we develop here is string gamma unsupervised possibilistic C median. This is actually a generalized version of unsupervised possibilistic C median in the numerical numerical part. So the objective function is going to be something like that. Since we cannot use any other distance, we have to use a Leeuwenstein distance. It's going to the objective function is going to be based on the Leeuwenstein distance. So this is the membership value of string sequence K in cluster I, and M is the falsifier, and the second part is just another part that makes this equation to be a possibilistic C median. And for the update, membership is this equation. So we just generalize from the regular one. But when we calculate a string cluster prototype, since this is a string, so we cannot use any mean or average stuff. So what we need to calculate is we need to calculate a fuzzy median string. So the fuzzy median string is something like this. So the median string is actually a string that has the summation of the distance to every other string in the cluster, the minimum summation of the distance to every string in the cluster. So that's the median string. So, but in our case, we use a fuzzy, so that's why this equation has to multiply with a membership value UIK to power 2m, which is a falsifier. And then the median string SCI is actually the one that give you this summation, the minimum of this summation. So that will be that string that will be a prototype of the cluster. But when we run the algorithm, we found that if we use every string, then the string that we get is not give us the best result. So what we use is we use something what called modified fuzzy median. This actually has been in the literature, so we just pick it up. So in this is actually we have sigma, which is a femodioid, over all the alphabet set. So the prototypes actually the string that are inside is free monoid. So monoid. So we actually select this first, and then it's still be the one that give this equation the minimum. So it's actually algorithm for the calculation of the prototype. So then in the Psi language, we use string gamma UPC median to create a prototype for each side. So each side will have more than one prototype. When the test string come in, what we calculate is we calculate fuzzy k nearest neighbor. Just like before, like we select k nearest string, and then we calculate ui of the string s for every class. And if the one that give us the highest ui, then the testing will belong to that class. Okay. So this is just like this. This is when we do the Psi language, we found out that Psi language for each language is different. Like Thai Psi language will be different from American Sign Language or India Sign Language. So it's gonna be different. It's not the same. So like this one is for grandfather. So from this whole video, we create a strings sequence. So this is a string sequence for that video. And first off, we only use 10 hand sign, which is represent from elder, grandfather, grandmother, gratitude, female, male, grad, thank you, understand, and then miss. So for each hand sign, we select what called keyframe. So like this keyframe, we have 27 for this keyframe, and we call this keyframe as a character A. And another 27 keyframe for this symbol, which is a character A1, something like that. So, and then we create this as and put it in what we call a signature library. So in our signature library, we have several keyframes for each character, and we have several characters. Okay. And then when we run an algorithm, we need to create a symbol for this frame, right? So what we do is that we use a zip algorithm to find a match between a keyframe that we have and then an image that want to find a keyframe. And then this is the zip algorithm, right? It's just do what zip does. And then for each keyframe, we have 128 dimension zip, what called zip feature. And then at that feature, then we need to find a match, right? Since we have several keyframes for one character, so what we do is that we calculate what called average match. So the number, which is average match, will be equal to number of match key point of a symbol, and then we divide with the number of keyframe of the symbol. So like in this frame, we have a value for each character, right? So the one that give us the highest will point us to the character that we want. So in this is actually the highest will be here. So it match with the character B. So it means that this keyframe is represented by character B. So we did that for all the frame that is select from the video. So we get a symbol sequence. And then after that, we run our algorithm on that data set, and then we get about 90% on average. If we use the training and the testing data is designer dependent. But if it's signer semi-dependent, signer semi-dependent is meaning that when we select a keyframe, we select from a subset, a set of a subject. But the person that the subject that we use to create a multi-prototype is different or is the same as the person that we use for testing, but it's going to be different person from the person that we use to create a keyframe. So that we, what we call signer semi-dependent. So in that case, we get 80%, around 80% on the average. But for signer independent meaning that the person, the subject that we use for the testing are different from the person that we use to create a keyframe and the person that we use to create a multi-prototype. So it's independent. So what we get is about 77% to 80% on the average. So that is for the Thai sign language. So now we want to know if what if we use this same algorithm on a different data set like American Sign Language data set. So we just get this American Sign Language from this site, RWTH Boston site. So it has several words like that, and each word it has a minimum sequence length. The minimum, you can see that the sequence length of the video is different, and the number of signer that they use for that video is different also. So this is the keyframe that we select. So like this keyframe represent character A. We have only 4 keyframes. For character A1, we have 8 keyframes, like that. So and then we just select it from train data. And this is the rest of the keyframe that we have in the signature library. So then when we run our algorithm, the number of the word that we use, since we need to use 31 word that we use. So what we get is about 80% on the average and 91% on the average in the classification. So 88% is when we do the leave one out strategy. For 91% is that we combine the training and validation set. This is on the average for both training and the data set, training and validation set. So you can see that even though we have string gamma, we still can create or develop a classifier to do the string gamma classification, and it gives us a comparable result. And in this case, since we create a multi-prototype from a string sequence, right? So prototype string sequence has the symbol that we know that it's gonna map into what, like in this case, in our symbol sequence, we know that each character map into what kind of sign. So when we have the whole string, we will know that the sign that are inside the prototype, what are the shape of it. So this is kind of like a little bit more advantage than regular calculation. So this is the end of our talk. So of course, I cannot do this work by my own. So all the work that I present here is actually, I need to thank two boys and girls who is currently and previously a member of Computational Intelligence Research Laboratory in Chiang Mai University. And all the funding that I have from the government funding or the faculty funding or the university funding. So final remarks for me is that a facet theory is actually can be utilized in creating feature, developing classifier, and all other things. Actually can do information fusion and stuff other than that also. And it can be also applied in many applications in your life. So thank you for listening. Do you have any question at all?
Thank you, Dr. Sansanee. That was a wonderful talk. So before I invite questions from our listeners, I would like to request our organizing secretary, Dr. Mili, to actually introduce Dr. Sansanee because we are all new to her. So
Oh,
I think she has a brief introduction before we start the question session.
Yes.
okay.
So, Dr. Sansanee, Wiriyakul received the
Yes.
engineering degree in electrical engineering from the Chiang Mai University, Thailand in 1993. The MS degree in electrical and computer engineering and PhD degree in computer engineering and computer science, both from the University of Missouri, Columbia in 1996 and 2000 respectively. After receiving her PhD degree, she worked as a postdoctoral fellow at the Computational Intelligence Laboratory, University of Missouri, Columbia. She is currently an associate professor in the Department of Computer Engineering and an associate director of the Biomedical Engineering Institute, Chiang Mai University, Thailand. Dr. Sansanee is a senior member of the Institute of Electrical and Electronics Engineering, IEEE. She is an associate editor of the IEEE Transactions on Fuzzy Systems, the IEEE Transactions on Neural Networks and Learning Systems, Engineering Applications of Artificial Intelligence, and ECTI Transactions on Computer and Information Technology. She was the editorial board of several prominent journals. She was a general chair of the IEEE International Conference on Computational Intelligence in Bioinformatics and Computational Biology, CIBCB 2016. She was a technical program chair organizing committee in several major conferences, including the IEEE International Conference Fuzzy Systems. She is also a member of several important IEEE CIS in technical committees. We are very thankful for her for making time for us. Thank you, ma'am, for sharing your valuable findings with us.
Thank
And
you so much for having me today also. I hope it's helpful.
yeah, sure, it was quite informative. Even I have some few questions to ask.
Okay.
Okay, fine. So anyone else who can ask, who want to ask any questions to Dr. Sansini? So we have a question in the chat box.
Okay. So what is the question?
Gaurav Banerjee has asked, is there any way of fuzzification of features which have finite number of discrete values?
Yes. You mean like if you have a feature and you want to falsify it, right? So yeah, there are many algorithms that you can falsify your feature, and after you falsify your feature, then the algorithm that you will work on it, we have to be uh into the domain of a fuzzy set calculation. So actually, I have a many algorithm that can do the classifier on of a vector with a fuzzy number also. So it's not that you can have only a vector of number that you run an algorithm on. You can have a vector of fuzzy number and you can create an algorithm to run on it also. So is that help?
Yeah.
Is it okay?
Mr. Gaurav Banerjee, do you have any other questions? Or anyone else having any other questions? Gaurav Banerjee says, thank you, ma'am.
Okay.
Anyone else? So that I can ask some. I have few more questions.
Hello,
Oh, sorry.
hello,
Yes. Yes.
madam. Uh, in sign language translation system, uh, in that case, geometric feature extraction, how much helps?
The what? Here?
Hello.
Yes. What is the question in this
Ye-
application? Right?
Yes, sir. Y- Hello,
Yes.
madam. In sign language translation system, we are extracting features, okay,
Mm-hmm.
from hand.
Mm.
So, in that case, geometric feature, how much helps us?
Oh, I didn't do any of that. What we did is just we just feed the image and do only shift calculation here. Here in this image, we just feed it in. We didn't do any pre-process or any post-process at all. After we feed that image into the algorithm, the SIP algorithm, then we only calculate the matching character from it like that. So we don't use any other algorithm at all. We don't do any pre-process at all.
Okay.
Okay, ma'am. Anyone else? Ma'am, Ordhendu Acharji has a question. Can
Yes,
you
there is
please?
one more question on the chat box. In
Yes,
chat.
Ordhendu Acharji. He asked, can you please explain me what is the difference between bipolar fuzzy set and intuitionistic fuzzy set?
Oh, that I haven't looked at it yet. So, cause to be honest, I didn't look at intuitionistic fuzzy set at all. So I cannot. I'm not a good person to answer that question. Sorry.
Ma'am, you have this robot navigation from hand-drawn images, right?
Yeah.
So is there any way so that it can be operated or at least can be interacted by some non-expert person?
Do you mean if non-expert person want to use it, right?
Yeah.
Yes, because actually the algorithm is not that. I mean, everything in that algorithm is not that simple, but it's not that hard. So it is actually easy to follow because what we did is we only use a fuzzy inference system and then um yeah. Yeah, and when we put it on the defense robot,
Yes, ma'am.
they can also use it easily. So it's not that hard at all. So
Okay. So is there any trade-off between this real-time spatial mapping or the speed and between this?
okay, um, let me think. When we put it on the real robot, there are some delay, but the delay time is not it's not high. It's less than one second for the robot to think. Because when we draw a map
Yeah.
and the robot translate a map into a command, that is less than a second. And then when the robot walk, it has to think in real time. Otherwise, it's going to hit the obstacle. So the trade-off is kind of like a minimum. I don't think it's going to be that high.
Okay. So is that basically a landmark matching or any kind of spatial relationship finding kind of thing?
It's landmark matching because in algorithm we assume that we know what the landmark, where is the landmark. So it's kind of like a landmark matching before we do the hand draw map. I mean, when we translate the hand draw map, we have to know what the landmark that we're talking about, where it is in the map actually beforehand.
Okay. And one more question, ma'am. I'm sorry.
That's okay.
I'm just a little interested. In this facial image or facial expression recognition,
Yeah.
yeah, you have this. You've said that for anger, disgust, and sadness, the
Mhm.
accuracy level is little less from other expressions.
Oh,
It has,
one.
does it has to do anything with the facial features or anything like that?
Yeah, I think it has to do with the facial feature. Which one? What? This one. Oh, this one, right?
This one, really.
The one that is the lowest is sadness. Yeah, because the sadness in the data set is kind of like a little bit. They not the image is not that sad. I mean,
Okay.
the face of the sad is kind of like a little bit like a normal face, a neutral face, thing like that. So that's why when we do the gradient thing, it's not that different from a neutral.
So for this kind of facial expression recognition, we need that the face must be some distinct deformations, right?
Right. Yes. Yes.
Okay.
So that is one of the advantage for this algorithm. Yeah,
Yeah.
that's correct.
Thank you, ma'am.
And you're welcome.
Anyone else have any questions?
Uh, I think there are no more questions. So on behalf of the organizing committee, I once again express our deep sense of gratitude to Dr. Sansanee uh, of Wiriyakul. I think I pronounced your name correctly.
Yeah.
Yeah. So we will be eager to have you in connection in future, so that our students and scholars will gain a lot from you. And thank you once again lending us your uh, valuable time and sharing your knowledge. So we were actually enlightened by your talk. I hope our scholars and students also gain a lot of knowledge. So thank you once again, and
Okay,
we'll
you're
we'll keep in
welcome.
touch. We'll keep in touch.
Okay, okay.
Thank you. Thank you.
Thank you for having me.
Now, I request any announcements to be done for the second session from Dr. Mandal, Ardhandu Mandal, or Dr. Mili Ghosh. Is there any announcement to
Yeah,
be
sure,
made?
sir. As the regular one, our second session will start or scheduled to be start from 5 p.m. So I request all the participants to join beforehand so that we can avoid the last minute chaos. And I again need to mention that all the participants have to join all the 6 sessions in order to get the certificates. And you have to fill up the feedback form, which we will provide just at the end session. And please get back with the feedback form so that we can process your certificates along with. So thank you once again for all of you to join this session.
For your kind information, ma'am, the talk was live streamed on YouTube, so you can watch it yourself later on also.
Okay, thank you.
We'll send you the link. Thank you.
Okay, you're welcome. Goodbye.
Goodbye,
Goodbye,
ma'am.
goodbye,
Thank you.
goodbye, goodbye. So I think we can end this session here and meet at 5 p.m. beforehand.